In our study of kinematics, momentum was the final quantity that we studied. Likewise, with rotation, angular momentum will be our final quantity before moving on to a new topic in physics. Angular momentum is defined by its equation, much like linear momentum. And the symbol that we use for angular momentum is an L. We'll use a lowercase l for a particle and a capital L for larger objects. So starting with the particle, our angular momentum is equal to the cross product, r cross p. Or another way of writing that would be m times the quantity r cross v. So this has a similar pattern to many of our other angular quantities, where it is the radius, which is what we'd call that r vector, times our linear quantity, which is that linear momentum. R in this case is a vector that starts at the axis of rotation and points to the particle. An important note here is that the particle doesn't actually have to revolve around an axis of rotation to have angular momentum. More specifically, a particle could be moving in a straight line and still have angular momentum. Now that might seem like a really strange concept to be discussing, but it'll come into play when we start looking at conservation of angular momentum. Now, as we know, all of our objects we study are not particles. And so we can talk about having a group of particles. And in that case, we'd use a capital L for our angular momentum, and it's just the sum of the angular momentums of each individual particle. One other important fact that I missed there is that our units here, much like our units for linear momentum, is kind of a longer expression, kilograms meters squared per second in this case, which is just our unit for linear momentum times meters. Just like for linear momentum, we do not have an abbreviation for this unit, so we just have to stick with the longer version. Now that we've talked about angular momentum for a single particle as well as for a group of particles, we then move on to talking about a solid object. I should say solid object, they're not solid particles. Sorry about that. In that case, you can't use our equation r cross p because all of the mass is not located at the same distance from the axis of rotation. So instead, when we have a solid object, we'll be using the equation that the angular momentum is equal to the moment of inertia times the angular velocity. That equation will simply give us the magnitude, so we'll only plug positive numbers into that equation. We'll use the right-hand rule to give us the direction. Specifically, we're going back to that right-hand rule that talked about using kind of a thumbs-up sign, where you curl your fingers the direction of the angular speed, and your thumb gives you the direction of that angular momentum. A couple more facts about angular momentum. Now, when one of the most important laws in physics is Newton's second law. We use that over and over again. And so we've learned that actually 3 times already. We've learned 2 different linear versions. The first one, which is that one that we think of probably the most when we get Newton's second law, is that the net force is equal to the mass times acceleration. But we also learned, back when we learned linear momentum, that Newton actually originally wrote his second law in terms of momentum, the fact that the net force is equal to the change in momentum, or really the derivative of momentum with respect to time. Then we move on to rotational forms of this law, and we have already learned that the net torque is equal to the moment of inertia times the angular acceleration. So our fourth and final expression of Newton's second law falls under this rotation version and mimics kind of our second version of Newton's second law, which says that the net torque is equal to the derivative of the angular momentum with respect to time. One last fact about angular momentum, and that is its conservation. Basically, if the net external torque that's on a system is 0, so that doesn't mean that there's no torques, but that if we add all the torques together, we get 0, then the angular momentum of the system is going to remain constant, no matter what changes take place within the system. So you may have something rotating, and perhaps something gets added to your rotating object, or something gets taken away from your rotating object, or perhaps your rotating object changes its shape somehow. That would mean, despite all these changes, the angular momentum of that system remains constant. We use this theory to explain why Ice skaters start spinning really fast when they pull their arms in on a spin, or why when one object hits another, they can start rotating, perhaps. We'll, of course, apply this law in many different scenarios so that you can understand the full importance of it. So that's just a quick introduction to angular momentum. We will do lots of practice with it, and if you have any questions based on this video, make sure that you bring them to class.